Well, thank you all for being here. Welcome to the second in our series of Snow Talk. We have a very exciting guest today, Martin Schneebeli, who I think I first came across Martin's work when I discovered the WSL, which I won't attempt to say. It's an acronym in German, but Institute for Snow and Avalanche Research. When I was just starting to do some research about snow. And man, Martin is very prolific. He's been studying snow for over 30 years. He's been working with the Snow and Avalanche Research Institute, he's based in Davos in Switzerland for a long time. And he's been so generous with his time and contribution to this project. So I'm super grateful that he agreed to come and talk to us today. And he also did something very, very wild and cool recently, where he spent, I don't know how long he was on the ship for, but there was this expedition that it was a ship that spent a year in the Arctic. And he went on that expedition for maybe the whole thing, maybe just part of it. I'm not sure actually, but he pretty wild and cool. And he was studying snow and ice and the relationship between those things. And maybe he'll talk a little bit about that. I'm not sure. And so when we first met, and if I asked him if he'd be interested or willing to do this, I guess I'm very coming at this from more of like from an art perspective, and clearly super interested in the science behind these things. But I asked him, what is the kind of snow that we want to see? Kind of like curious, if there's like an ideal snow. And his answer, well, he laughed first and he said, all snow has different properties that are good, and that there is no ideal snow, which I thought was great. So without further ado, I will pass it along to Martin.
Thank you. Thank you, Anne. I share my screen. Okay. Today I speak how to make the invisible visible, the challenge of understanding snow. And what is the challenge? So ice is what's the content of this talk? Ice is one of the most transparent natural minerals, so crystals for human eyes. So when we observe snow, this poses many challenges because it's quite hard to describe and measure a transparent material. And snow appears to us humans more or less uniformly white. And because it's uniformly white, we have to use destructive methods to get an approximate view how the snow is structured. And that's maybe, as you will see, or that is also a problem to understand snow. But in recent times, we have new methods, so we can make visible the invisible snow. And I start with the point about ice and try to explain why is ice not always transparent. What you see in this figure is the wavelengths of light.
Oh, Martin, we can't actually, I don't think you've advanced your slides, so we can't see what you're talking about. I just see the first slide.
Oops.
Sorry to interrupt you.
No, that's fine.
There we go, perfect.
Now you see the second. So ice is not always transparent, I say, and I try to explain that. And now you see this figure on the x-axis, so on the bottom, you see the wavelengths of light. And in this range between blue and red, that's the wavelengths we see as humans. And on the y-axis, so on this axis, is how much light of a specific wavelength is absorbed per meter. So when it's a small number, then it's very little light, and when it's a large number, it's almost all light. And we see that when we look here, so in the greenish, we see this absorption is about 1/100th of the light per meter. While when we go here to this wavelength of 900 nanometer, which is called near infrared, it's almost 1,000 times more. So it's 10, so only a tenth of the light arrives at 1 meter distance. Now, what does that mean? It means that ice is very transparent in our visible, what we see as visible light, but it's much less transparent in the near infrared. And that's, we will use this property later when we try to see snow structure or the snow. Now, how can we imagine that this blue light is going very deep into ice? This is a drill hole in Antarctica, and we covered this drill hole with a big tarp, so no sunlight could come in, and then this light, so the blue light goes deepest into the ice, is least absorbed. Then this hole is illuminated in this blue light. And I think that's a very nice illustration how ice is not the same way transparent to all wavelengths. Now, when we look on snow or ice, then we see that on the surface it may appear very whitish. And when we put the box like this on this blue ice, so we there is much less light scattered at the surface, then we see all the structures in this ice. So this is called blue ice, it's in Antarctica. And we see already that when light is reflected, then the ice gets whitish, and when it's transmitted, then we can see certain structures. And here I took a picture where we see the change from ice to snow. So here is the ground, and ice is the ice which is melted out here is transparent. We see still the ground through the ice, and then it becomes more and more snowy, so smaller particles or smaller structures, and then it becomes white. And that's a very fundamental property, that when the structures are large, they are more, for our eye, more transparent, and the smaller structures the more white they appear. Now, why is snow white and not transparent? Because we have seen ice is very transparent. So when a light ray touches a snow structure here symbolized as a sphere, it gets deviated in a certain angle, and then it goes in another direction, touches another sphere, goes, and then in the end, its sunlight is coming back. And this is called scattering. And that's the reason why snow appears white. And why is snow now not red? It's because at the wavelengths we see as humans, ice is always very little light absorbing. Even when we have larger snow grains or snow structures like here, we don't see the effect that more of the light is absorbed in these ice structures than when less light is absorbed in the smaller ice structures. We don't see the difference with our eyes. And now I go a little bit away from the snow and I go to the polar bear, because the polar bear is also white. And his fur is white because its hair is transparent. But thanks to this transparent fur, it warms its black skin. Now, let's have a look. And I saw actually during the Mosaic expedition a polar bear, and I think these are really very interesting and majestic animals. But you see here also that the white of the polar bear is almost as white as snow here on the sea ice. Now, how does polar bear fur looks like? And when you look at these thin hairs, they are really almost transparent. You could think of a special kind of snow. And when we go even closer, we see that this hair is about 100 micrometers, or a tenth of a millimeter. And this is a diameter as typical snow has. It's almost transparent, so it has similar optical properties as snow has. Now back to the snow. How can we measure snow? We imagine often that snow looks like this almost perfect snow crystal. It's hexagonal, it has these dendritic structures, and it's single particles or single crystals. But this structure exists only for a very short time. Snow on the ground looks like this three-dimensional model. So we have this three-dimensional printed model at our institute. And what you see here is that all these ice crystals, so these are ice crystals here, are connected to each other. And this connectedness makes a very intricate, complex structure. And when we look at many different types of snow, so these are different types we measured in the snow during what's called an intercomparison, so where many different instruments were measuring the same snow. We see that there are many different types of snow, each has its own structure. So we see snow is really a three-dimensional structure. And we can even, with a special technique, we can measure where is a crystal or what is really a single crystal. And we see that, for example, this blue rounded particle is a crystal and is then connected to a next crystal in this turquoise color, and then to this orange color, and so on. So these are all single crystals connected to each other. When we do snow measurements in the field, we have to scratch from this complex structure, small particles. And here is an example from the surface of sea ice in the summer, because it's nice to see how large there the crystals grow. And we see here large columnar crystals, and here large rounded crystals. And when we look at the three-dimensional structure, it looks quite different. So what's then important for the physics, how light is reflected, is the image of this, is the three-dimensional image and not the single particles. So we have really a challenge in snow measurements. And the question is, can we identify, measure precise properties when we have this picture? Here it's again a rounded snow. And we see here it's, for example, a crystal, and this is connected to another crystal, but then the connection to this crystal is broken. And we have no idea that the whole thing looks like that. So like a three-dimensional structure. So traditional snow observation is like looking at the ruins of a building. And here I have a picture taken from the internet. This is a reconstructed temple in Selinunte in Italy. And below we see how this temple looks now. And it's easy to imagine that it's very hard to reconstruct, to get an idea of this building by looking at these ruins. And that's the challenge we have in snow science. So we have to, what I call here tricks. We have to look at the snow where its whiteness disappears. So we have to make snow visible. And one way is that we can use X-ray computed microtomography. And I will explain that later. And we have another trick. We can look at the larger scale of snow by near-infrared photography. Now here in the back is X-ray microcomputer tomograph. And this is a box, and we can put in this box such samples as shown here. And then the box or the X-rays and the detector measure a three-dimensional image. And here I have an example, just a small cross-section from such a sample. And the white frame here shows the part I used then to make the three-dimensional reconstruction. And we see that this frame here is about 1 centimeter by 1 centimeter. And now I have many such slices. Actually, every in this case, every 30 micrometer, I have a slice. And from all these slices, we can reconstruct now this three-dimensional image. And suddenly we see that this strange cross-section or this particle consists of a very complex shape. So we have this here, these structures. Here we have these plates, and we can identify how these particles are connected. When we do this tomography, we can, as I said, measure precisely the geometric properties. And one property that is traditionally used is called grain size. It's the largest extent of a snow particle. And when we look at these two different tomographies, they look quite different. The grain size here is about 1 millimeter. The grain size here, the traditional grain size, is about 0.2 millimeter. So we would say the traditional grain size here is smaller than for the rounded snow. On the right is smaller than for the decomposed, so the old new snow here, which has longer structures. But what's now important for the optical properties is the specific surface area or the optically equivalent diameter. And here now this measure is completely different. For the decomposed snow, the optical equivalent diameter is 0.12 millimeter, and it's almost 3 times larger for the rounded snow. And that means that this snow here is has a much higher albedo, is reflecting much more light than this snow here. Not in the visible spectrum. In the visible, so what we see as humans, these two snow would almost look the same, but in the near infrared, they look different. Here it's also a nice image what we can do with this X-ray tomography. This is surface hoar, so a few millimeters large on decomposed snow, so on old fresh snow. And we can see now how these structures lie on this other snow layer and all the orientation of this surface hoar. So we get really a very detailed image of the snow. So as you may have already guessed from the previous images, snow is transforming. Snow is transforming, or it's called metamorphism, because snow is a high temperature material. It has a very high vapor pressure. And as soon as there is a temperature difference, a temperature gradient within the snow, then it starts metamorphosing. And with this tomography, we can do in the lab a time-lapse observation and look at the snow metamorphism without disturbing. And here it's a movie showing this metamorphism. The time at the bottom is in hours, so it's a 3-week observation, and we see that the snow becomes something very different within these 3 weeks. It's in constant change. And to come back to the comment of Anna, what's the ideal snow? There is no ideal snow. Snow is always changing. Oops. So now we have seen that when we look at the microstructure with this computed tomography, we can see a lot of details. But it's really quite a small sample. And when we would like to look at a larger snow profile, at a larger area, we need a different technique. I mentioned that in the near infrared, so again, in this region, which is blue colored, in this wavelengths, which is blue colored around 900 nanometers, ice is not so transparent anymore. What we have here on the y-axis is the albedo. And we see that in the visible light, the albedo is very high. So that's why for us, snow is white. When we look at this near infrared, then we see that depending on the structural size, on this optically equivalent diameter, small particles or small optical equivalent diameter has a higher albedo, a higher reflectance than coarser structures. And this property can now be used to see snow in different grays. So near infrared photography makes sometimes black closest to white. But the effect is now, the physical effect why this works is when we have small particles like here, then in the small particles, the absorption is smaller than in the large particles. And we see here the same number of transitions. So it's 1, 2, 3, 4 particles where the light is going through. Here it's again 1, 2, 3, 4 particles. But in these large particles, the light has to travel a longer distance. And when light travels a longer distance in the near infrared, it gets more absorbed. So we see then these two snows in different colors. And here is an example. So we have the brightest snow at the top. The brightest snow is at the top because it's the smallest snow structures. And then we see here in between something quite dark. This is a buried surface hoar. And then we see here something which is a little bit more gray. That's a bit the older snow structure. And then we have here something which is quite dark, and that's depth hoar. So using this near infrared photography, we see different snow layers, although they would appear completely white in a normal photography. With a bit of image processing, and that's when we change from the gray to any color scale, we can even measure this optical equivalent diameter. So we can measure the structural size of the snow. And these two images also illustrate that we can see in great detail the different layers. We see also if a layer is homogeneous or a layer is disturbed. We can even combine then near-infrared photography and computed tomography. We see here these very dark layers here are actually very thin structures when we take then from this snow pit samples and look at them in the tomography. So I hope that you could get something about why and how snow is white and how we can make snow visible. Ice is really a super transparent material for our human eyes, but we can see shades of gray with the near-infrared camera. Snow is white because it's a sum of scattered and reflected light. If you would illuminate snow with red light, it would become perfectly red. So it's just because sunlight has all these colors in quite an equal distribution, and we see that as an equal distribution, that snow is white. X-ray tomography not only sees broken bones, it also sees the microstructure of ice and snow. And it's a very powerful instrument to see really these very fine details and structure of snow. Thank you, and if you have questions, they are welcome.
Thank you so much, Martin. Wow, yeah, that was great. Really wild, those infrared photos. They kind of look like landscape paintings or something. Anyway, yeah, I'd be glad if people have any questions. We can open it up. I definitely have some questions. I guess I'll just start because I have a few questions. I'll start with my question about I guess in the beginning you were talking about how in order to get a to see the invisible, right? To see the invisible snow, you have to use destructive methods. And I guess, what do you mean? What does that mean exactly? In terms of like using destructive methods, you mean you have to like sample it and then like destroy the snow, or what does that mean?
Yes, that means when you just look at the snow from far, you don't see the structure because it's more or less transparent and it's all overlapping these ice crystals or these ice structures.
Mm-hmm. So
we take a small sample and put it on a crystal plate, on a black plate, and then observe with magnifying glass. But for that, we have to destroy the structure.
Okay.
So we see only the particles, and we don't see the connectedness.
Okay. Okay. Yeah, I see. That makes sense. I'm thinking about the snow metamorphism or snow metamorphosis like movie or something, or like thinking about those the tomography, I guess that's what it was, of seeing the like connectedness rather than seeing the particle. So I think I understand a bit better now. Thanks. That's interesting.
I have like a cluster of questions. that will hopefully make sense. But okay, here we go. Is it density that determines the absorption and wavelength of ice, or is it like a combination of that, like temperature and age? In any case, it would seem that the absorption and wavelength maybe continuously change. So does that mean that they could move, like snow and ice could move in and out of the visible and invisible spectrum, like in nature? Does that make sense?
Um, so snow consists of ice. And I'm not sure if I understood your question completely, but the absorption of the ice is a physical constant. So in the visible, the absorption of the ice is always the same. But it changes with increasing wavelengths. So the blue light is almost not absorbed by ice, and that's why I showed this blue image where we drilled this hole into the ice, and all the red light and the yellow light and the green light all became absorbed in the ice, and only the blue light came into this hole. And for snow, now snow is you can't see the snow structure by eye because we can't see in a range of the wavelengths where the absorption of the ice is sufficient to make a difference. I don't know if that was your question.
I don't really know either, to be honest, but I think that answered it. I guess like the most like concrete part of the question is like, can snow or ice like move in and out of the visible and invisible spectrum like in nature? Or does that make sense? Or like is the only way like does invisible snow is invisible ice or snow like forever invisible, I guess is the question.
For us humans, snow is always invisible. So if we, and that's the trick with the near-infrared camera, because the near-infrared camera is like a third eye for us. It measures in a wavelength which we can't see.
Got it. Thank you.
Thank you.
Great question, Monica. Monica's the other half of this project. She's a designer. She's yeah. So that was her. Any other lingering questions? I know there must be because there aren't a ton of science-oriented people on this. So oh, Cody, do you have a question? I see there's a person that looks like they have a question.
I had a question.
Okay. Oh, yeah. Go ahead, Dave.
Is metamorphosis of snow it happens regardless of the conditions that the snow is in?
Yes, or almost yes. So if we could keep snow below -100 degrees Celsius, then there would be almost no metamorphism. But because snow on Earth is very close to the melting point, we have always there is always metamorphism. And because in nature there is almost a temperature difference in the snowpack, the metamorphism is quite fast.
Thank you.
I have I have a comment, which is maybe I just wanted to say that when you were showing that the snow metamorphism like time lapse, that was super amazing. It's really cool. And because you had made the comparison to like the building or something, or like finding like ruins of a building and trying to like understand the building's structure. Yeah, it was interesting because to me that time lapse was like, it was like taking like really small bits, you know, and building something, because like it gets bigger and bigger as it elapses, which I don't know. Yeah, yeah, as like visual material, I thought those things were like really rich, and so I appreciated that. I loved all your slides, actually. Your slides are great. And the polar bear encounter too. I saw that you guys had people when you were out on the expedition. I read that you had like 6 people on polar bear watch at all times.
Yeah, there were always a few people on polar bear watch. So each group outside had one person which had to do polar bear watch.
Wild. Does anyone else, any other questions?
I had one more question, Anna, if I can.
Yeah, of course.
So in the metamorphosis video, would that technically be called melting? Is that what's happening?
No, it's not melting. It's so the experiment was at -8 degrees Celsius. And what happens is that the upper part of the ice structures in this movie are slightly warmer than the bottom part of the overlying ice structure. And then the ice of these crystals sublimates and gets deposited on the colder part of the crystal. But it's not melting. So it's from solid to vapor to solid.
Thanks.
I guess I wanted to say one more thing, which was that, so what you were saying about like the destructive methods of like, like kind of isolating the particle and not being able to see the connected quality of the snow. So like that aspect of snow, the connectedness of the crystals, does that mean that that's always invisible to us? Like there's no way we can really see that?
Yes, there is no way we can really see that.
That's so
we
cool.
can see that by bare eyes.
Yeah, we can't see that. We need assistance to see that.
Yes.
Okay. Interesting. Yeah, that's super interesting. Okay, well, I don't know. Any other takers? Any other lingering questions out there?
Oops.
I hear you.
Can you hear me?
Hello?
Yeah.
Yeah.
Hi. Hello. I'm wondering how you got so interested in snow in the first place. I missed the very beginning. Maybe you addressed that.
No, I didn't address this point. But yeah, I started with forest-snow interaction, and then snow became more and more interesting because so little was known how snow is really structured. And then I got fascinated for, yeah.
One thing led to another, I guess. Thank you.
Are you working on anything, any new projects right now? What are you working on right now? What kind of research are you doing?
Yeah, at the moment I'm working on the mosaic data, so on the data from this expedition.
Cool. All right. Well, I guess we'll wrap it up here, but thank you so much. This is really wonderful, and I learned a lot, and I feel like, yeah, it's very in support of the project that I'm trying to create here. So I really, really appreciate your time, and yeah, thank you so much. And thank you everyone for coming on a Saturday. Well, it's a Saturday morning on this coast. So, but yeah, take care.
Yeah.
And maybe sometime we can meet in person. I'd love to.
Yes.
All right.
Okay. Thank you.
Thank you. Bye-bye.
Bye-bye.